So the divergence theorem in space, there is also a two-dimensional version, says under certain conditions, the flux integral, and we should call this a flux integral of a vector field over a closed surface. The surface here is a closed surface, meaning it encloses a solid, a three-dimensional solid. It's not the same idea as a closed set way back in chapter whatever it was, 10. It's not quite the same idea as a closed set. Chapter 12, maybe, where we were talking about optimization of functions, and I mentioned the extreme value theorem, for example. And closed and bounded sets were important. That's not the exact same idea. The closed surface idea here is the surface, two-dimensional surface, encloses a three-dimensional volume. It's not like just one plane or one triangle like we just did. It could be a tetrahedron made up of sides that are four triangles. That would be a closed surface enclosing a certain volume. The flux integral is of the vector field F, written like this. And this is something I have mentioned before. The easiest way to imagine this is to imagine F as a velocity vector field, meaning that the arrows in three dimensions represent velocity vectors of molecules, effectively, like water molecules, fluid particles, if you prefer. Anytime a water molecule is at the base of one of the vectors in the vector field, that's a velocity vector for that molecule at that moment in time, whatever moment in time it happens to be. It's a static vector field. It's not changing over time. Some fluids, the vector field does change over time. The simplest situation, I don't know, with a stream that's moving in a uniform way, the velocity vector field is effectively constant. That could be in meters per second or centimeters per second, perhaps. N doesn't affect the units. ds is a surface area element, a small amount of surface area. Its units would be, if this is centimeters per second, this would be square centimeters, giving you a product here that's cubic centimeters per second, an amount of fluid, a volume per unit time. And the integral doesn't affect the units. So the adding up those small fluxes, volume per unit time, gives you the total flux across the surface. In your imagination, you pretend the surface is a permeable membrane, like a net, a very fine net that water molecules can easily pass through. And it stays fixed in its shape. It doesn't wobble. Idealized situations. The divergence theorem says this equals the triple integral of the divergence of F with respect to the volume of the solid. D is the solid. And the divergence of F is, for a three-dimensional vector field, if F has components M and P, then the divergence is a scalar quantity, mx plus ny plus pz. It'd be nice to try to understand the divergence as a rate of change. I don't really have time for that today. Maybe a little on Friday. It is a kind of derivative of the vector field, made up of a sum of partial derivatives. Yeah, never forget those are partial derivatives. That's partial m partial x plus partial n partial y plus partial p partial z. Somehow it's measuring near any point how the vector field is changing. It's just kind of mysterious how it's measuring that. And as hinted at in the book, it's measuring whether the flow tends to be out of small regions or into them, or some in and some out, so the divergence is zero. If you assume this solid D is a tiny little region, you could approximate this triple integral as a product. Assuming D is small. How small is small? We don't ever be real specific here. Just imagine, if you want to get extreme, you could say it's microscopic. A microscopic volume, you could approximate this triple integral as the value of the divergence of F at some point P inside D, that's inside D, times, this is a number, times the volume of D, excuse me. Just as an integral of a regular calculus 1 or 2 function is the area under the curve, and you could approximate the area under the curve by a rectangle, the area of a rectangle, base times height. That's something going on here analogous. That's kind of like the height, that's kind of like the base. Value the function times the volume instead of value the function times a small length for a regular one-dimensional integral. And again, the divergence theorem is saying that this equality is true, so that would be true when D is small as well. And this integral gives you the flux. So this is saying when you got a small region, the flux is approximately the divergence times the volume. In other words, the divergence is flux per unit volume. The divergence of F at the point P is approximately flux per unit volume. I shouldn't write that way. It's flux divided by the volume of D. The flux being that flux integral. The volume, if the solid was a sphere, then you could just figure out the formula, the volume, by doing 4/3 pi r cubed. If the solid was a really tiny cube, just do x cubed, take the side lengths and cube them. So it's a way to interpret the divergence near a point. In the case where you got a clear source, for example, as you would have, for example, for this vector field, x, y, z, near the origin. See how Mathematica does as far as graphing this. It is vector plot 3D. So this is supposed to be some sort of three-dimensional vector field that's going to try to plot. I have no idea how good it's going to look. With arrows in 3 dimensions, where the vector field is x, y, z, effectively you're pointing radially away from the origin in all directions. That's not too bad. The origin is in the middle of the box here. It's effectively a source with respect to this vector field. If you imagine those are velocity vectors for a fluid, it's like there's somehow magically water coming into the system at the origin and then moving radially away. Of course, that could never happen in real life unless you attached a wormhole to the origin and sucked in water from an alternative universe or something. But if you pretended it was realistic, it would be a source. And that corresponds to the fact that the divergence of this is 1 + 1 + 1 is 3, a constant 3, positive. So in fact, the triple integral over any volume would be 3 times the volume. And that would be the flux across any surface. The triple integral would be 3 times the volume. Now, that would be the flux. Whatever volume you have, the flux is 3 times the volume. Numerically speaking, its units would be different. The volume would be, say, in cubic centimeters, and the flux would be in cubic centimeters per second, say. I think to apply this, and physically speaking, I think you effectively need a constant of proportionality that's 1, that's got the right units to make the units work out. But this vector field, x, y, z, has constant divergence of 3 everywhere in space. So the flux being 3 times the volume of any solid near the origin applies anywhere. How do you make sense out of that? Because there's only one source seemingly at the origin. And the way to make sense out of that, and this is the final thing for today, is to say, okay, I'm not near the origin anymore. But I got these vectors at points, maybe the origin's down here, maybe that's 0, 0, 0. But I'm thinking about these vectors in the vector field along some sphere not centered at the origin. Why is the flux still positive here, as it has to be because of the divergence theorem? It's because the vectors on this side of the sphere are longer than the vectors on this side of the sphere. And that's why more water's flowing out per unit time than is flowing in. Now, again, we're ignoring questions about whether it's realistic or not. But that's what the divergence theorem would tell you for that vector field. And you could imagine a pretend fluid that does that. Is that useful? I have to ask Dr. Stein if it's useful or not. I do know that fluids where the divergence is always 0 have a special name. They're called incompressible fluids, which seem like they'd be more realistic than compressible fluids. But I don't know, maybe some fluids are somehow compressible. You can take them in a certain amount of volume and you can compress them easily and they stay in the same kind of state. I don't know. Maybe this can be realistic to some degree. When you're applying these things in physics and engineering to fluid mechanics, electricity, and magnetism, they really are more applicable in a theoretical sense. They represent truths about reality, fluids, electric fields, magnetic fields. Like Gauss's law, isn't that a law about magnetic fields or electric fields? Gauss's law is a reflection of like the divergence theorem applied to electric fields. So that's probably their bigger importance. We're just trying to get used to them by actually doing calculations to help us believe them. Is maybe you might say our main purpose is believing these things are true. Through examples, not proofs.